Well, now let's examine radar losses. We'll go over some examples, and then we'll summarize. The system loss terms in the radar equation are great in number. And if you just look at them, on the transmit side, you've got a huge number here. The radome, that bubble you see in covering many radars from the elements. The circulator, the TR switch, the waveguide feed. The waveguide itself has losses in it. The antenna's efficiency, beam shape, low-pass filters on the transmit, the rotary joints. While the antenna is going around, you have the energy come in, and there's a loss in a joint, a microwave joint there. Scanning losses, atmospheric losses, quantization losses, and field degradation losses. And in the receive side, there's an even greater number. There'll be, on the receive time, the radar energy coming back into the circulator, the waveguide feed, the waveguide, the combiner. There may be different waveguides combining to one central focus that will go into the receiver, a receiver protector that protects the receiver from getting jolts of energy from the transmitter, reflections that it shouldn't. Rotary joints also it's going through. The transmit-receive switch, the antenna efficiency, the shape of the beam, the fact that it's scanning by the target, the fact that when you make a Doppler filter lobe, you're not in the center of the filter, Doppler straddling lobes and range straddling lobes, the weighting you put on the filtering system in the Doppler filtering. You don't have an ideal receiver filter. The constant false alarm rate thresholding method has a loss, quantization. There are atmospheric losses, and then on top of all of this is you run a radar for a long time, and you're going to have what we call field degradation losses. It ain't going to work the way you do it the first day you put it out in the field. Different components they're not like your hand calculator that just works and just dies. There are enough analog systems in the transmitter and in the receiver itself that they will slow down in efficiency. Rust will occur. All kinds of different physical things, and these are what we call field degradation losses. They all have to be taken into account. And you can imagine, remember I showed you if you want the range to go down by a factor of 2, 12 dB in losses, what you incur. And if you get a half of a dB loss in each of these on transmit and receive, you're way down. So your range, your effective range of the receiver, of the whole radar, can be drastically impacted by each of these not coming in to play to the specified amount by 1/10 or 2/10 of a dB. And there's one fundamental rule. You don't get plus losses. They always count on the negative term, negative side of things. And one thing I'm going to point out to you, a lot of the times we'll calculate the atmospheric losses based on a normal atmosphere. And sometimes the atmosphere is not normal. There's anomalous propagation. You know, an antenna goes around so many times and it starts to wear and can have little juncture points, and the losses can go up after a while. So there are lots of different things that just happen in time, happen in weather, happen in years of use. Now what we're going to do is go over, for that huge list, we're going to talk a little bit about each one, and we're going to sometimes have another visual, but give you an idea. We have the beam shape loss. The radar return from the target with a scanning radar is modulated by the shape of the antenna beam as it scans across the target. That is to say, if the antenna is rotating, and let's take an exaggerated example, it transmits every 2 pi rotation, and every 2 pi it does that in about 5 seconds. If you have a beam with a little over a degree, about 20 pulses will impinge on, say, a large chimney a smokestack, of a power station or something. And those pulses, the pulse of energy that's sent out, are going to be modulated by the antenna beam as the antenna beam moves across the target. And so you're going to get the return from each of these pulses is going to be amplitude modulated by the antenna gain and the motion. And what that will do is it will do two things. It will lower the reflectivity out at the edges, but it will also, that amplitude modulation will give rise to the ground clutter not have a stationary object, that chimney, not having zero Doppler. It'll give a spread, well, it'll be zero main Doppler, but it will spread the Doppler return. And that will leak into the Doppler filters of your system. It's something that has to be taken into account. So scanning antenna losses. Phased array radars is set up so that the radar goes out and looks slightly overlapping at different points in space. And when the phased array antenna sends out a beam that's as close to the target as it can get, it's not always straight on the center of the target. And that's so for a phased array you can have the gain in the beam is less than on boresight. We have the input to the system noise temperature. We talked about some of that before. The local RF noise, the galactic noise. It can be, local RF noise can be a transmitter on a power distribution line that's 300 feet from the radar. Receiver noise factor, the receive waveguide losses, and the antenna ohmic losses. That is to say, as electromagnetic energy goes through the antenna elements in certain kinds of antenna systems, it'll give off some heat because they're not perfect conductors. And it will give off ohmic losses, and so there'll be losses there that have to be added in. Now, let's look over some other major terms. Waveguide and microwave losses, particularly in the transmit waveguide losses, including the feed, the rotary joints, the circulator, and the duplexer. I believe next is yes, here it is, a rectangular waveguide attenuation. Okay? And this is taken from John Velakis' handbook, reference 7, these 2 pages. These are for the different frequency bands where the waveguide is made out of aluminum, brass, and silver-clad copper. For the dominant mode of transmission, transverse electric 1-0, you'll learn about that later, in gigahertz, these ranges of transmitter frequency, which these modes will accommodate, have attenuation which can be as little as a 20th to a 30th of a dB for 100 feet of waveguide, UHF, down to 6 dB to 4 dB per 100 feet of waveguide at these frequencies, at higher frequencies. So at higher frequencies, you can have fair losses in your waveguide. That says you want to put your transmitter as close to the antenna as possible, if you can. If you have a very high-powered transmitter, you don't want a 50-foot of waveguide at X-band, because that'll give you a significant loss in power, reaching the antenna to be. Next would be signal processing losses. And that has to do with the weighting and range and Doppler, that you weight the shapes of those passband filters, the ranges that you look at. There are the A to D quantization losses, the adaptive thresholding losses, and the fact that your target may be halfway between one range cell and another. That gives you a loss there. Those are all come under signal processing losses. And then there's this a little known but often neglected term called the lens effect loss, that refraction in the atmosphere causes spreading of the beam and thus degradation of the signal to noise. Here we have what that loss can be, loss for point targets, as a function of slant range and on elevation angle. So if you're very close to the surface of the Earth, you're at a very low elevation angle, you can have at a slant range of 1,000 miles, 1,000 nautical miles, you can have a very significant loss in the lens effect loss. And it's independent of frequency, and it's only significant for targets of very long range and low elevation angle. And then atmospheric attenuation losses. These are the attenuation in the atmosphere as the radar travels through, the radar beam travels through the atmosphere, and it's a two-way loss. Now here we see the two-way attenuation through the entire troposphere as a function of radar frequency, and for 1, 0, 1, 5, and 30 degrees. And as you can imagine, the attenuation is greatest at 0 degrees, and the least down the bottom at 30 degrees. Now, that's through the entire atmosphere. A lot of times, if you're an aircraft, on an aircraft as your target, its distance is much less than through the entire atmosphere. And these curves, these are for X-band 10 gigahertz, which is 10 gigahertz. The attenuation, two-way in dB to the target, where the target to radar distance is, say, 200 miles. If you're at 200 miles and your elevation angle of your beam is 2 degrees, you're going to suffer 2.7 degrees of attenuation at X-band. And there are sets of curves in Blake's book and in the Radar Handbook, which you'll see, that you can look these things up. And I think this is the last set we're going through. The bandwidth correction loss. The receiver is not an exact match filter for the transmit pulse. The integration loss. When you add up pulses that are looking at a target, if you non-coherently integrate them, that's not as efficient almost all the time as integrating them coherently. And if the target fluctuates as a function of aspect angle, and that changes relative to the target, if you're looking at the target within a dwell time and the target moves a fair amount, you can have fluctuations of the target. You'll see that when we talk about radar cross-sections, and how it can oscillate quite quickly as a function of aspect angle for complex targets when there are many scattering sources, and so you have a lot of scattering sources interfering constructively and destructively with each other as the aspect angle changes. That can cause the target cross-section to fluctuate a lot. There's a fluctuation loss that has to be taken into account. And then a field degradation, a margin. Characteristics of the radar that deteriorate over time. It's not unreasonable to design a radar with a 3 dB margin in it. You can get water in the transmission lines, and that will attenuate. Weak or poorly tuned transmitter tubes. They just get older, and you don't run the 4-minute mile when you're 60 years old. And those transmitter tubes can wear out, and so they might be off, their peak power might only be down 5%. But it's a little bit, and you got to worry about it. And deterioration in the receiver noise figure. So these are all the different kinds of losses that can occur in a radar, and you have to take them into account, and very, very carefully if you're building a radar. If you're doing it, as I say, back of the envelope, you get within the ballpark. But when you're really putting a radar together, every different group of people building the different subsystem have to have an allocation of losses which they believe they'll get, and they have to be held to their losses. Because you can see there are 8 or 10 different subsystems, and then the atmosphere and the target, and each one of them loses a half a dB, your detection range will drop a huge amount. So that you really have to, if you're a radar systems engineer looking at the whole picture, you have to keep track of all the different losses everywhere in your system, and make sure that every component that comes in is tested, that it met the loss requirements that were put in its procurement or when it was built. A disaster can happen cumulatively. Even though one little subsystem, it might not seem to hurt that much. Well, now we move on to a couple of examples of the radar equation, which we'll do in detail. The first is that of an airport surveillance radar, and they all have pretty generic characteristics. We're going to do the calculation sort of back of the envelope, zeroth order, just to give you the feel of how these calculations are done. And then we'll look more carefully at a C-band range instrumentation radar, and so you can see at the next level of depth how the equations, what reasonable numbers flow forth in the equations. Now, let's look at this example in the form of a problem. We want to show that a radar with these parameters below get a reasonable signal-to-noise ratio on a small aircraft at 60 nautical miles. Small aircraft being a single-engine, two-seater Piper Cherokee that's about 1 meter square in cross-section. And the range is going to be 60 nautical miles. The peak power of these radars tends to be 1.5 megawatts. We're going to take 1.4 megawatts. Duty cycle, quite small, 0.6 microseconds pulse width. And the inverse of that, 1.67 megahertz is the bandwidth. The frequency is at C-band, 2.8 gigahertz. Rotation rate, 12 RPM. That's about 5 seconds approximately. The pulse repetition rate is 1200 hertz. And the antenna size is about 4.9 meters by 2.7 meters high. The azimuth beam width is 1.35 degrees, and the system noise temperature is 950 degrees Kelvin. Using this data, particularly for the frequency, we get a wavelength of 0.103 meters. Gain, putting in that area, is 4 pi a over lambda squared, which gives us 15,670, which is 42 dB. But actually, there's a huge amount of beam shaping loss in that the shape of the antenna is deformed so that there's a lot of gain up at high elevation angles, and so that when planes are in close and high, there'll be a lot of energy on those targets. And so that the actual gain comes out, when looked at accurately, is 33 dB. And the number of pulses per beam width, as the beam, which rotates on a mechanical scanning antenna, there'll be 21 pulses at this 12 RPM, which will scan by a target, given that RPM and those pulse repetition rate. And we're assuming the losses in the system of 8 dB. So here we have the equation for the signal-to-noise ratio for the dwell, for the single pulse, and here are the numbers. So we want to, the first thing, and it's probably the most important mistake and thing to watch out for, because it's the mistake I mostly make, is get everything in MKS units. So we transform the 1.4 megawatts to 1.4 times 10 to the 6 watts. 33 dB is 2,000 in natural units. It's going to be squared up here, so we put it in twice. Lambda is squared, so that's 0.1 meters and 0.1 meters. And then the cross-section on top here of 1 meter squared. Now, on the bottom we have 4 pi cubed, 1,984. And then next we have the range to the 4th power. Notice I've transformed the 60 nautical miles to 111 kilometers, which is 100,000 meters. And we give that to the 4th power. Then Boltzmann's constant, followed by the noise temperature, the system temperature in degrees Kelvin. And then the losses, which we usually talk about in dB, in natural units, that 8 dB transforms to 6.3. And then the bandwidth, the noise bandwidth, is 1.67 megahertz. And here we have it out in hertz, so all the units will cancel out. And when you put all the exponents together and all of the numbers, you grind them through, you get first these numbers, And I put them in this form so that you can do it yourself. And then you get 5.6 times 10 to the 10th over 4.15 times 10 to the 10th. And that's 1.35 or 1.3 dB. So we have a signal-to-noise ratio per pulse of 1.3 dB, and we're integrating 21 pulses. And that gives us a gain of 13.2 dB, integrating the pulses, the 21 pulses. And then I'm assuming a coherent integration, so that the signal-to-noise ratio per dwell is 14.5 dB, plenty well enough for us to get decent detection on this target. Okay, now let's move to look at the dB method for doing exactly the same calculation. We take the same numbers that would go into the equation, and what I do is just draw two columns, one the guys that are in the plus column and one in the minus column. And let's just go down. Well, 1.4, you got to multiply it by 10 to the 6th, and that comes to be, and that's up on top, so that stays at 61.5 dB on the top. The gain squared, well, you multiply powers, so it's 66 dB, that's on the top. 0.1 meters squared for the wavelength, and so that's 10 to the minus 1 multiplied by 2, so that's minus 20 dB, so that'll go on the bottom with a negative. 1 meter squared, well, that'll be 0 on the plus side. 1984, the logarithm of that, that's on the bottom, so, but it's a plus number, but on the bottom, so it gets a negative 33 in the minus side. The range, which is a big number, in kilometers, 111 kilometers, so you got to multiply that times 1,000. But that we've got to take the fourth power of, and that's on the bottom, the denominator, so that's 201.8. Boltzmann's constant is a large negative number, but that's on the bottom, so it comes on the plus side when we take in dB units. And the system temperature, which is on the bottom, is 950. So that comes out to minus, because it's on the bottom of the equation, 29.8 dB. And as before, 8 dB just goes over as 8 dB. And 1.67 megahertz on the bottom goes to be 62.2, but you have to put it over in the minus sign because it's in the bottom. You add up the pluses, you add up the minuses, subtract them, and lo and behold, we get the same number, 1.3 dB, as the signal-to-noise ratio per pulse, which, in this case, we're assuming coherent integration. 21 pulses is 13.2 dB, and which gives us, again, our 14.5 dB. So you do it decibel units, you do a scientific notation, you get the same number. Okay, now let's move over to the issue of a C-band pulsed radar, an instrumentation radar with 6.5 meter dish, 1,000 kilowatts of peak power, and 1/10% duty cycle. What's the maximum detection range on a target with 0 dBSM cross-section, with a probability of detection of 0.9, probability of false alarm 10 to the minus 6, assuming a swirling case 1 target fluctuations, and a 1 microsecond pulse. So in this case, we want to calculate the range when we're given the probability of detection and the probability of false alarm and the type of fluctuations. Those will give us the signal-to-noise ratio from which we can back out and then calculate the appropriate detection range. We're going to be integrating 50 pulses non-coherently in this case. So now we look down and we want to get out the right signal-to-noise ratio per pulse. Now here's the curve of signal-to-noise ratio versus number of pulses non-coherently integrated for a swirling number class 1 target and a probability of false alarm of 10 to the minus 6. If it was just one pulse and all 50 pulses were integrated coherently, we'd have a signal-to-noise ratio of 21.2 dB in that one big pulse. not 50 pulses. But we're taking 50 pulses, and you can see if you go down to 50 pulses, in 50 pulses, there's be a net coherent integration gain of 17 dB. So we subtract off 17 dB from the total signal-to-noise ratio of 21.2, and we get 4.2 dB per pulse is what we're required to have. So if we take the radar equation in the dB form, and we put in the 4.2 dB, and then put in the frequency, we'll get out the wavelength, and the noise bandwidth, which is just a megahertz for a microsecond pulse, the 1,000 kilowatts of peak power, and there's a couple of other numbers, the system noise temperature of 9 dB of losses, and the system noise temperature of 598.2. And we'll see on the antenna efficiency is 65%, with a this is actually 6.5 meter antenna. It comes out to be 49.6. 49.6. And then you put in the system losses, and these are all typical numbers that you get, and that's how you get the 8.95 dB. And the losses on the input to the system noise temperature are these, and when you plug those numbers in, you get 598.2 for the total system noise temperature. The transmit losses, which are over here, are 1.3 dB, and they break down into these. And the signal to noise, the signal processing losses of 1.9 dB break down into these. And you get the attenuation loss off a graph. So that's how it all fits together. Now let's summarize. I'm going to make this summary in pieces. You can notice I went through an awful lot of numbers. The radar equation is simple enough that just about anyone can learn to use it and understand it. Just algebra and learning to use powers and dBs. But unfortunately, it's complicated enough that you can make algebraic errors very easily, very easily. I put these together with spreadsheets, do it once very carefully, triple check it, and then whenever I do the equations, I know I've got the algebra right. Okay? And the next view graph gives you really relevant things to do. You want to take a candidate equation and check that the dimensionalities are right. When you have the equation, see that the watts cancel the watts, the range to the fourth cancels the meters squared here and the meters squared there, and the bandwidth here cancels the hertz and other places, and the hertz and the peak power, which is an energy, and there's a joules here, which will cancel the other part of the energy, joules per second. See that they all, cancel out. And then check on the dependencies make sense. That increasing the range and the signal-to-noise ratio make the requirements tougher. Increasing the power in the antenna grain makes the radar more capable, and if you drop the wavelength in the cross-section, the radar's less capable. Now, what I want you to do is to just look at this. It brings together what we're going to study in the detection of signals and noise lecture. And that lecture concerns these areas. So what we do in the radar equation is we take the radar parameters, the range to the target characteristics, and the propagation of the medium, feed that into the radar equation, and that gives us a signal-to-noise ratio. Now, that signal-to-noise ratio is put in with the type of detection we're using, linear or square law, how the target fluctuates, or does it, is it a steady target, the noise statistics, Gaussian noise, or some backgrounds are other than Gaussian, and the detection thresholding mechanism, is it a constant detection mechanism or an adaptive threshold, which you'd have to plug losses back into this equation. And that will come out with a set of curves relating to the signal-to-noise ratio and these assumptions to the probability of false alarm and the probability of detection relating these. So the radar performance parameters and the design parameters are related through the radar equation. There are two different forms of the equation, search and track. And scaling the equation allows the radar designer to understand the parameters and to accommodate the different changing requirements and be very, very careful using sanity checks. I really advise the use of a spreadsheet. You check out once, then you don't have to worry about your algebra, which can very easily, we can all make mistakes by hitting the wrong button on a keypad or whatever. And compare those parameters you get with a real radar that has about the same size and characteristics, same power and aperture. It ought to be able to do the same thing. Here are the references we've used in this lecture. And I'd like to thank Steve Weiner and Claude Noiseau from Lincoln Lab, who have done a great deal of help in putting together radar equation lectures at the lab, and as well as ones I put together, and I've used some of their ideas. Now, homework problems for this lecture are to read over Chapter 1 and Chapter 2, the relevant sections that have to do with these problems. It'll be pretty obvious to when you look back. The first two chapters are good ones to sit down and read through. There's not an awful lot of them. And they're the core basis, not of the whole course. There's a lot more chapters than just Chapter 1 or 2, but these problems are taken from Chapters 1 and 2. We'll be covering pretty much all the material in Chapter 1 and 2, and most of it we've covered in this lecture. But some of the work on radar cross-section is more detailed in these chapters. We're going to have a separate lecture on that material.